You know, if you hand a toddler a wooden block, like let's say it's just a simple cube with the number 4 painted on it,
Right.
and you turn that block completely upside down, the toddler still knows it's a block.
Oh, absolutely.
Yeah, they still know it has a 4 on it, even if the number looks, a bit weird and top-heavy. They don't suddenly think the block has vanished from existence and been replaced by an entirely new, unrecognizable alien object.
They don't freak out.
Exactly. They have this innate sense of the world.
And that innate sense is actually a highly sophisticated mechanism in the human visual cortex. I mean, from a very young age, the human brain develops this intuitive understanding of object permanence.
Okay, object permanence, yeah.
Right, and spatial invariance, too. The object remains the underlying object, regardless of its specific orientation or, lighting or position in three-dimensional space. We intuitively separate the essence of the object from its spatial coordinates.
Right, but here's where it gets totally wild. If you take a standard state-of-the-art neural network, right, one of these massive artificial intelligence systems that can write a passable sonnet or pass a medical board exam, and you feed it an image of that exact same number 4, it works perfectly.
It nails it.
But if you take that exact same image and rotate it by just 90 degrees, the AI completely loses its mind. It fails spectacularly.
It's like the toddler suddenly screaming because the block turned into a monster.
Yes, exactly. It just completely breaks down.
Well, it is the absolute definition of a machine's blind spot in visual processing. We build these incredibly complex, deeply layered artificial systems that mimic brain architecture, yet they fundamentally lack the underlying geometric intuition of a human child.
Which is so crazy to think about.
It is. To the machine, every single pixel value has suddenly changed its geographical location on the grid.
Yeah.
So the input vector is completely alien. It doesn't see a rotated 4. It sees chaotic, unprecedented noise.
And that tension, right, between the messy, continuous reality of physical data and the incredibly rigid, discrete way machines are forced to learn. That is exactly the problem we are unpacking today.
It's a huge hurdle.
Welcome to this deep dive, everyone. Today, you and I are going to explore a massive hidden bridge. And I want to give a very special shout out right at the top here, because we are doing this deep dive specifically for you, the Bus Sigma Scholars of Edward Little High.
Ah, yes. The scholars requested this one.
They absolutely did. So listen up, Edward Little High, because we are diving into the bridge connecting the abstract, pure mathematics of geometry and symmetry with the absolute cutting-edge practicalities of artificial intelligence.
We're going to see how the exact same mathematical tools used by top-tier geometricians to solve million-dollar math conjectures are actually being used right now to fix that AI blind spot.
We are making neural networks smarter and way more topologically aware.
It is a genuinely beautiful convergence. I mean, for decades, pure mathematics and applied computer science just operated in total silos.
Right, never talking to each other.
Exactly. But right now, at the frontier of machine learning, the math of the physical universe and the math of the machine are starting to look identical.
So think of this conversation as a treasure map. And you, the listener, and especially our scholars at Edward Little High, you are riding shotgun with us as we chart this out.
We're pulling from a whole stack of materials today.
Yeah, we've got Bruno Ribeiro's deep dive lectures on neural network invariance, and that leads all the way to some incredibly heavy algebraic geometry papers from Bar-Ilan University.
We're talking sheaf theory, Sophic groups, and the legendary Hodge conjecture.
It sounds dense, I know. But we're going to break down exactly how these theories work in physical reality. Let's start with this problem of machine vision and that rotated number 4.
Sounds good.
So I was watching Ribeiro's breakdown, and he uses the MNIST data set. Now, for those who don't know, MNIST is basically the classic starter pack for AI training.
Yeah, it's tens of thousands of little black and white images of handwritten digits.
Right. Think of it as the hello world of machine vision.
It's a very controlled environment. I mean, each image is exactly 28 by 28 pixels.
Right. So if a standard multi-layer perceptron or even a convolutional neural network sees an upright 4 from that data set, it nails it.
Every time.
But rotate it, and it's game over. Now, I know the standard industry fix for this. Software engineers use something called data augmentation.
Which is basically brute force.
Exactly. You take your training images, and you just create hundreds of copies of them, rotated at all different angles, 10 degrees, 20 degrees upside down, and you just brute force feed all of those to the AI, too.
Which is incredibly computationally expensive, but yeah, that is the brute force approach. You are essentially telling the network, memorize this pattern.
Right.
Now memorize this slightly tilted pattern. Now memorize this upside down pattern. And that strategy actually works, provided you stay strictly within the specific domain you trained on.
But Ribeiro points out that this totally falls apart in transfer learning, right?
Exactly.
Like if you introduce a completely new shape that the AI has never seen before, say the letter C instead of a number, and you rotate that C, the network is completely lost again.
Because the network never actually learned the universal mathematical rule of rotation. It didn't learn geometry.
It just memorized a vast catalog of specific rotated pixel patterns for the numbers 0 through 9.
Right. It's like a student memorizing a math test's answer key instead of actually learning the quadratic formula.
That's a great analogy.
Yeah, if the teacher changes the numbers on the test, the memorizer fails instantly, but the student who knows the underlying formula passes easily.
So the AI has the answer key, but it doesn't know the formula. So how do we force the AI to learn the fundamental formula for a rotation?
To do that, we have to step away from computer science for a moment and borrow from a very old, very pure branch of mathematics called group theory.
Okay, group theory.
The goal is to build what mathematicians call G-invariant and G-equivariant neural networks. And the G simply stands for group.
Let's pause and define that, because when I hear group, I just think of, a bunch of people standing around.
A social group.
Right. But in pure math, a group is an incredibly strict, specific concept.
It really is. A mathematical group is essentially a collection of actions or transformations combined with a set of rules for how those actions interact.
Okay.
To qualify as a valid transformation group, it must possess 4 distinct properties. First is closure.
Closure. What does that mean practically?
It means if you take an object, apply one transformation from your group, and then apply another transformation from your group, the final result must be achievable by a single transformation that already exists within that group.
Okay, so if my group is rotating an object by 90-degree increments, if I rotate it 90 degrees and then I rotate it another 90 degrees, the result is a 180-degree rotation.
Right.
Since 180 degrees is in my group of 90-degree increments,
Yeah.
the group is closed.
Yeah.
I haven't, accidentally created a 45-degree rotation.
Exactly. You haven't escaped the parameters of the group.
Got it.
The second rule is associativity, which just means the order in which you group your sequence of transformations doesn't change the final outcome.
That makes sense.
The third rule is that there must be an identity element. There has to be a transformation in your set that does absolutely nothing, leaving the object entirely unchanged.
Like rotating by 0 degrees.
Precisely. It seems trivial, but mathematically, it's the anchor of the whole system.
Okay. And the fourth rule.
And fourth, and this is the property that trips up a lot of AI architectures, every single transformation in your group must have an inverse.
An inverse, meaning an undo button.
Basically, yes. You must be able to perfectly undo whatever action you just performed to return to the exact original state.
And this is where Ribeiro gave an example that completely changed how I think about this.
The scaling example.
Yeah, because I always assumed you could just apply this math to anything, like scaling an image. If I have a high-res photo and I scale it down by 50%, that's a transformation.
It's a transformation.
But Ribeiro says you cannot form a valid linear group out of scaling images. Why is that?
Think about the physical mechanics of scaling a digital image down. If you have a 1,000-pixel image and you shrink it to 100 pixels, what happens to the other 900 pixels of data?
Well, they get deleted. The computer just throws that information away to make the files smaller.
Right, so try to apply the fourth rule of group theory, the inverse. Can you perfectly undo that action?
Oh, I see.
If you take that 100-pixel image and try to scale it back up to 1,000 pixels, you don't get your crisp original image back. You get a blurry, pixelated mess.
Yeah, it looks terrible.
You cannot mathematically invert the transformation because the data has been destroyed. Therefore, scaling down and scaling up in that specific digital format does not form a valid transformation group under these strict mathematical rules.
That is wild. The absolute unbending laws of pure math dictate the physical limits of our computer code.
They absolutely do.
So we can't easily use group theory for scaling without losing data, but we can use it for rotation. Because, rotating a square image by 90 degrees doesn't delete any pixels, it just shuffles their locations.
Exactly. Rotation forms a perfect group. So how do we actually apply this valid group? Let's stick with the group of 0, 90, 180, and 270-degree rotations to the neural network so that it intrinsically understands rotation.
Right. How do we build that in?
First, we have to entirely rethink how the machine represents the image.
Because right now it's seeing a 28 by 28 grid of numbers.
And trying to perform the heavy linear algebra required for complex group transformations on a two-dimensional matrix grid is incredibly clunky. It's mathematically restrictive.
So what do we do instead?
To fix this, we vectorize the image. We take that 28 by 28 grid and we mathematically slice it row by row, stacking those rows on top of each other until we have flattened the entire image out into a single massive column.
So instead of a square grid, we just have one incredibly tall list of 784 numbers.
Exactly.
We've transformed the image into a 784-dimensional vector.
Which is, difficult for the human mind to visualize. A space with 784 physical directions.
Yeah, my brain hurts just trying to picture that.
But for a computer, it is computationally beautiful. By flattening the image into this vector space, our group transformations become simple, elegant, linear transformations called endomorphisms.
Endomorphisms. Now, I tried to look this up, got completely lost in textbook definitions. What does that actually mean in the context of our flattened image?
An endomorphism is simply a mathematical function that takes an object in a specific space and maps it back into that exact same space, preserving its structure.
Okay, so what does that look like for our 784-dimensional vector?
Well, you have an input image existing in this 784-dimensional space. You apply a mathematical transformation matrix to it, say the matrix that represents a 90-degree rotation. The output isn't some new weird data type. The output is still a 784-dimensional vector existing in the exact same space.
Oh, I get it. The object's structural integrity is perfectly preserved. It has merely moved within its home space. Okay, so we have our flattened image vector, and we have a group of transformation matrices. One for 0 degrees, one for 90, one for 180, and one for 270.
Right.
Now comes the million-dollar question. How do we build the neural network so that it is literally blind to which one of those 4 rotations it's looking at? We want it to see the 4-ness of the 4, regardless of the angle.
To achieve that, we use one of the most elegant tools in algebra, the Reynolds operator.
The magical Reynolds operator. When I was reading this section, I felt like I was learning a magic trick. Walk us through how this operator functions.
It is surprisingly simple in concept, but really profound in execution. The Reynolds operator is a method of mathematically averaging all the transformation matrices in a given finite group.
Wait, literally just averaging them, like taking the test scores of 4 students and dividing by 4.
Exceptually, yes. You take the massive matrix that performs a 0-degree rotation, you mathematically add it to the matrix that performs a 90-degree rotation, you add the 180-degree matrix, and you add the 270-degree matrix.
Just stack them all up.
Yep. Once they are all summed together, you divide that supermatrix by 4. You have created an average of all possible states in the group.
Okay, but what does an average matrix actually do to the neural network? If I multiply my image by an average of all rotations, doesn't it just blur the image into a weird smeared circle?
It would if you applied it to the image itself. But we don't apply the Reynolds operator to the image, we apply it to the neural network's internal weights, the mathematical filters the network uses to look at the image.
Ah, okay, that makes a big difference. Let's dig into that.
In a standard neural network, a neuron operates by taking an inner product, which is a type of mathematical multiplication, between its own learned weights and the incoming image vector.
Right.
Normally, during training, those internal weights can adjust themselves to be absolutely anywhere in that vast 784-dimensional space. The network is completely free to guess and check.
It just wanders around trying to find the best fit.
Exactly. But to make the neuron invariant to rotation, we take away that freedom. We mathematically force the neuron's weights to live exclusively inside a very specific sub-basement of that space.
And a sub-basement is called an eigenspace, right?
So specifically, we restrict the weights to the left eigenspace of the Reynolds operator, corresponding strictly to the eigenvalue of 1.
Okay, I'm going to need you to unpack that. If I'm the listener, my eyes just glazed over at eigenspace, corresponding to the eigenvalue of 1. What is a physical analogy for this?
Sure. Think about shining a flashlight on an object to cast a shadow on the wall.
Okay, I'm picturing it.
If you have a long rectangular box and you rotate it in your hands, the shadow on the wall changes shape dramatically. It gets longer, shorter, wider.
Yeah, depending on how I hold it.
But imagine if you had a perfect sphere. If you rotate a perfect sphere along its center axis, the circular shadow on the wall never changes. The The shadow is invariant to the rotation.
Because the sphere is perfectly symmetrical.
Exactly. In linear algebra, when a matrix acts on a vector, it usually stretches it, shrinks it, or knocks it off its axis, just like the changing shadow of the rectangular box.
Right.
But sometimes a specific matrix applied to a specific vector only stretches it, without changing its fundamental direction. That vector is an eigenvector, and the amount it stretches is the eigenvalue.
So if the eigenvalue is 2, the matrix just stretches the vector to be twice as long,
Yeah.
but it still points in the exact same direction.
You've got it. Now, what if the eigenvalue is exactly 1?
If it's multiplied by 1,
Uh-huh.
well, then it doesn't stretch at all. It doesn't change direction, and it doesn't change length.
Yeah.
It is totally unaffected by the matrix. It's like the sphere's shadow.
Precisely. By projecting the neural network's weights into the eigenspace corresponding to the eigenvalue of one of the Reynolds operator, we are guaranteeing a mathematical certainty.
Which is,
If you take those specific weights and you multiply them by any of the rotation matrices in our group, you just get the exact same weights back. They are perfectly stable. They cannot be altered by rotation.
that is brilliant, because the weights are the eyes of the network. If the eyes themselves cannot be changed by the rotation math, then when those eyes look at the rotated image, they calculate the exact same inner product.
Exactly.
The mathematical output of that neuron is mathematically guaranteed to be identical, whether the input image was upright, sideways, or completely upside down.
The first layer of the network essentially puts on a pair of highly specialized, polarized glasses that completely filters out the spatial orientation. The neuron literally cannot see the rotation anymore. It only sees the pure geometric essence of the number 4.
And the craziest part of Ruggiero's tutorial is that he shows you only have to do this incredibly complex mathematical restriction on the very first layer of the network.
Right, because once that first layer extracts the invariant essence of the image, the output passed to the deeper layers of the network is already free of the rotational noise.
And the rest of the network doesn't have to care.
It doesn't. It can just operate like a normal, highly efficient neural network, doing what it does best. You aren't forcing the algorithm to slowly learn the laws of spatial physics through brute force memorization. You are hard-coding the laws of symmetry directly into the fundamental architecture of the system.
That's an unbelievably elegant solution. You define a group, you use the Reynolds operator to average it, you find the stable eigenspace, and boom, your AI understands spatial geometry.
But
Yeah, here's where the story takes a massive turn, where we hit a brutal mathematical speed bump. Ribeiro takes this beautiful, flawless logic, and he tries to apply it to a different kind of AI architecture. He tries to apply it to graph neural networks, or GNNs.
which are becoming arguably the most important type of neural network in modern data science. We use them for everything from mapping complex social networks to predicting how new pharmaceutical drugs will bind to proteins.
Right, because a graph isn't a neat little grid of pixels. A graph is just a collection of nodes, like individual people on a social network connected by edges, like the friend connections between those people.
And Ribeiro points out that with a graph, the symmetry we care about isn't rotation. You can't really rotate a social network. The symmetry we care about is permutation.
Permutation. Give me an example of that.
Think about a molecule. If I hand you a mathematical graph of a water molecule, H2O, I might label the oxygen atom as node 1 and the 2 hydrogen atoms as node 2 and node 3. But that labeling is entirely arbitrary. I could label the oxygen as node 3. The physical molecule doesn't care about my labels. It is still water. The structure is the structure regardless of the order in which I list the nodes in my spreadsheet.
So a graph neural network must be invariant to the permutation of its nodes. If I shuffle the list of users in my dataset, the AI shouldn't suddenly think the whole social network changed. It has to recognize the same underlying structure.
Logically, you would approach this exactly the same way Ribeiro approached the image rotation.
Right. I was literally thinking, oh, I know how this ends. We have a permutation group, all the different ways you can shuffle the nodes. So we just use the Reynolds operator. We average all the possible permutation matrices. We find the eigenspace with an eigenvalue of 1. We project our neural network weights into that space, and we're done. The AI is blind to the shuffling.
It sounds perfect.
But when Ribeiro actually runs the code live in his tutorial, it's a complete catastrophe.
It really is. It is a mathematical collapse of epic proportions.
Walk us through what actually happens to the AI's learning capacity when he applies the Reynolds operator to a graph.
Well, when you have an image grid, The Reynolds operator filters out the rotation noise, but leaves a massive, rich dimensional space for the neural network to actually learn the shapes.
Right.
But a graph is different. The permutation group of a large graph is overwhelmingly huge. I mean, every possible way to shuffle every single node. When you average all of those permutation matrices together using the Reynolds operator, the math is so aggressive that it flattens almost everything in the vector space.
Flattens it how?
Out of thousands or millions of dimensions, the rank of the resulting invariant space collapses down to exactly 2.
Wait, 2.
Yeah.
Not 2,000, not 2%. Just literally the number 2.
Exactly 2 dimensions. You are left with exactly 2 parameters for the neural network to adjust and learn from. One parameter represents the diagonal of the weight matrix, and the other parameter represents literally everything else off the diagonal.
Let me stop you there, because I want to make sure I'm understanding the gravity of this.
Go ahead.
If making a graph neural network mathematically invariant means we compress its entire learning capacity down to just 2 measly dials it can turn, doesn't that make the whole concept practically useless?
Unfortunately, yes.
Like, how on earth could an AI possibly learn the intricate multi-layered complexities of a billion-user social network, or the 3-dimensional folding structure of a complex protein if its brain is mathematically restricted to 2 parameters?
It can't. That is the stark reality. We are hitting a hard wall with basic group theory here. The elegant solution that works flawlessly for rigid, uniform spaces like a grid of pixels in a photograph fails completely when applied to the messy reality of graphs.
But why? What is fundamentally different about a graph that causes the math to break down so violently?
It comes down to homogeneity versus heterogeneity.
Okay, unpack that.
An image grid is perfectly homogeneous. Every pixel is structurally identical to every other pixel. They're just organized in a uniform lattice.
Right.
But real-world data, especially data represented as graphs or complex manifolds, is incredibly heterogeneous.
Right. Nodes have different numbers of connections, different data types, different local environments.
It is highly irregular. To process that kind of chaotic data without collapsing the learning capacity of our network, simple global averaging, which is what the Reynolds operator does, is far too blunt of an instrument. We have to upgrade our geometry.
We have to level up. We need a math that can handle the messy, irregular real world without flattening it into nothingness.
We have to move out of the realm of simple group theory and step into the much more advanced domain of sheaf theory.
Which brings us into the second major phase of our deep dive. I was reading this paper titled Sheaf Theory, From Deep Geometry to Deep Learning.
A fascinating read.
Now, I had absolutely never heard the word sheaf used in a mathematical context before reading this. I mean, I thought of a sheaf of wheat. But the way they explain it is actually incredibly intuitive if you fundamentally rethink what data is.
To truly grasp the power of a sheaf, you first have to understand the fatal flaw of a standard graph structure. We just said a standard graph is a collection of dots, the nodes, and lines connecting them, the edges.
It's essentially a skeleton, a stick figure.
Exactly. And standard graph neural networks operate on an underlying assumption called homophily.
Homophily?
Yes. Homophily is the assumption that nodes that are physically connected to each other are fundamentally similar in nature. If node A is directly linked to node B, the algorithm assumes their underlying data is probably alike, and it can average them together.
And I can see why software engineers built it that way. Because homophily works really well in specific, curated domains. Like predicting political affiliation on social media. If I follow 5 politicians from a specific political party, and I interact with their posts, the network can safely assume I probably belong to that party. The homophily assumption works. My node is similar to the nodes I connect to.
But the authors of the paper point out that in complex, dynamic, real-world systems, like vast knowledge graphs or physical sensor networks, data is wildly heterogeneous. The homophily assumption becomes a huge liability.
Right. If node A is an air pressure sensor mounted on a weather balloon, and node B is a humidity sensor on the ground, and they are mathematically connected in a weather prediction model, their actual data types are entirely different.
Completely different units, different scales.
Right. One is measuring millibars of pressure, the other is measuring moisture percentages. If the AI assumes they are similar just because they share an edge, and it tries to average an air pressure reading with a humidity reading, the math is disastrous. It's garbage in, garbage out.
Precisely. You cannot simply average heterogeneous data. So how does a sheaf fix this structural flaw? A sheaf upgrades the mere skeleton of a graph by attaching a unique vector space to every single node and every single edge.
Okay, visualize this for me. Instead of node A just being a flat dot on a whiteboard, what is it now?
Imagine a mathematical space hovering directly over that dot. In sheaf theory, this is sometimes called a stalk.
A stalk, like the stem of a plant.
Kind of, yes. It is a full vector space that contains all the possible data states and dimensions relevant strictly to that specific node. The air pressure node has a vector space containing the mathematical language of pressure. The humidity node has an entirely separate vector space containing the language of moisture.
And this is where the paper clicked for me. I was trying to come up with an analogy, and I realized a sheaf is basically just a giant, messy, multinational corporation.
Oh, I like where this is going. Walk me through it.
Okay, think of the global corporation as the total graph. Each individual department is a node.
Okay.
You have the heavy engineering department in Munich, Germany. You have the flashy marketing department in Tokyo, Japan.
Mm-hmm.
And you have the hardcore finance department in New York.
3 totally different environments.
Right. They're all connected. They all work for the same company. But their local environments, their vector spaces, are totally different. Engineering speaks German and uses metric units. Finance speaks English and uses US dollars. Marketing uses yen and measures success in social media impressions, not dollars or millimeters.
So they are fundamentally heterogeneous nodes.
Right. And if the CEO, who represents the standard graph neural network, tries to just blindly average a German engineering blueprint with a Japanese marketing campaign, it's a disaster. Homophily fails.
So how do they communicate? Because they clearly have to exchange data to function as a company.
That is the genius part of the sheaf. To connect these different vector spaces, the sheaf places specialized mathematical tools along the edges connecting the nodes.
The restriction maps.
Yes. These tools are called restriction maps. And a restriction map is basically just a linear transformation that acts as a highly specialized translator.
That is an exceptionally accurate analogy. The restriction map takes the data from the local context of the German node, translates it into a neutral, shared language that lives on the edge connecting them, and then translates it into the local context of the Japanese node.
So the restriction map takes the engineering specs in millimeters and mathematically converts them into a budget requirement in yen so the marketing team can actually understand it.
Exactly.
The sheaf models not just the connection, but how the data itself must morph and translate as it travels from one local context to another.
And because this translation system is rigorously defined by linear algebra, we can use it to compute something incredibly powerful about the entire network. We can compute sheaf cohomology.
Cohomology. I swear, I feel like mathematicians just invent words that sound like magic spells to keep the rest of us out. Let's break this down without the textbook jargon. What is cohomology actually measuring in our corporate sheaf?
Well, in the broader field of algebraic topology, cohomology is a toolkit for measuring the fundamental overarching properties of a space, specifically looking for holes or structural invariants.
Okay, looking for holes.
In our applied sheaf theory, it allows the AI to analyze the global state of all this messy, heterogeneous data at once. We look at a sequence of these vector spaces, and we compute what is known as the zeroth cohomology group. Mathematicians denote this as H0.
H0. And what does H0 represent in the real world?
It represents the space of global sections. In plain terms, H0 is total system-wide consensus.
Consensus, meaning everyone agrees.
Meaning the data is perfectly harmonized. It is a state where if you take the data from any node in the entire network and you translate it through every single restriction map along every single edge, the translated data perfectly matches the local data of the receiving nodes everywhere all at once. There are absolutely zero contradictions.
Okay, so back to the corporate analogy.
Yeah.
H0 is that incredibly rare mythical moment when engineering, marketing, and finance all completely agree.
Yeah.
The engineers design a part for 10 euros. It perfectly translates into an $11 budget for finance, which perfectly aligns with the 2,000 yen campaign in Tokyo. The translations yield zero mathematical conflicts.
Precisely. That perfect harmony is an element of H0. But as you might imagine from your corporate experience, in vastly complex systems, perfect inherent consensus is incredibly rare. There is usually friction, data conflicts.
All right, finance says we only have $5, but engineering says it costs 10 euros. That's a conflict.
And that is exactly where the next level of the math comes in. The first cohomology group, denoted as H1.
Let me guess, H1 is the mathematics of disagreement.
In a way, yes. H1 represents what algebraic geometricians call syzygies.
Syzygies. Okay, that is an elite Scrabble word right there. What is a syzygy?
Simply put, a syzygy is a relation between relations. In the context of our sheaf, H1 measures the exact dependencies and the fundamental obstructions that are actively preventing that perfect H0 consensus. It mathematically quantifies the fundamental topological holes or structural contradictions in the data medium.
Okay, this is where the AI application blows my mind. Because if H0 is total corporate consensus, what does it practically mean for our neural network when it calculates that H1 is non-zero, when it finds these syzygies?
It's a game changer.
Is the AI actually detecting fundamental structural contradictions in the data that a normal graph network would just blindly smooth over and ignore?
That is exactly what's happening. That is the profound advantage of a sheaf neural network. Think of a standard homophily-based graph neural network like a terrible middle manager.
Oh, I know a few of those.
Right. When the engineering team and the finance team disagree, the terrible middle manager just averages their two numbers together, forces a completely fake, smoothed-out consensus, and reports that up the chain. The nuance and the reality of the disagreement is completely wiped out.
The middle manager destroys the data to make the graph look pretty.
Exactly. But a sheaf neural network, by rigorously calculating H1, explicitly detects and models those structural contradictions. It doesn't just average them away.
It acknowledges them.
Yes, it mathematically understands exactly why the data doesn't agree, where the translation breaks down, and what structural holes exist in the network. It preserves the complex geometry of the disagreement.
That is incredible. It gives the AI a level of, critical thinking.
Yeah.
But how does the AI actually run this calculation? The paper talks about computing this consensus using something called a sheaf Laplacian and a process called heat diffusion. Now, I know what heat diffusion is in physics, but how does an algorithm diffuse heat?
This is where we borrow a brilliant metaphor from thermodynamics. Think about heat moving through a physical object. If you have a solid iron rod and you hold a blowtorch to one end, that end gets incredibly hot while the other end is cold.
Right, a temperature gradient.
But nature doesn't like gradients. Nature wants equilibrium. So the heat will naturally flow, it will diffuse down the rod, moving from the high temperature areas to the low temperature areas. It will continue to flow dynamically until the entire iron rod reaches a perfectly uniform temperature, a state of thermal equilibrium.
And mathematically, nature is just doing calculus to figure out how that heat flows.
Specifically, the physical diffusion process is continuously optimizing a non-negative quadratic function. It is mathematically seeking the lowest energy state of the system.
So how do we put an iron rod inside an AI?
In a sheaf neural network, we define a mathematical object called a sheaf Laplacian. In standard calculus, a Laplacian operator basically measures the difference between the value at a specific point and the average value of its immediate neighbors. It measures the tension.
Okay, the tension between nodes.
Yes, our sheaf Laplacian is a massive matrix that captures all of that tension, but it includes the structure of every single restriction map, every translator, across the entire graph.
So it's a map of all the localized disagreements.
Exactly. And by applying the mathematical equivalent of heat diffusion to this sheaf Laplacian, we allow the disparate data to naturally flow across the network. The data pushes against its neighbors, translating dynamically back and forth through the restriction maps, continually adjusting itself until the mathematical tension is relieved. The system naturally settles into an equilibrium.
And that equilibrium is H0, the consensus state.
Yes. The heat diffusion naturally finds the optimal global section.
This is so cool. The AI doesn't have to rigidly calculate a top-down answer. It just lets the data flow through the translators until it settles into a natural harmony. And the paper points out that this isn't just for fixed, rigid data structures. You can actually use this sheaf Laplacian trick to discover a hidden manifold, like a hidden shape to the data that you didn't even know existed.
This is where sheaf theory borders on differential geometry. In complex data sets, the points often don't just sit in a flat space. They exist on a curved, multidimensional surface called a manifold.
Right.
By defining specific types of matrices on the edges of our sheaf, specifically orthogonal matrices, denoted mathematically as ON, we can treat the edges not just as translators, but as paths for parallel transport.
Parallel transport. Okay, try to give me a visual for that.
Imagine you are standing on the equator of the Earth, holding a spear pointing straight north.
Okay, I have my spear.
You walk perfectly straight up to the North Pole. You haven't turned the spear in your hands. Then you sidestep, keeping the spear pointing the exact same way relative to your body, and walk down to the equator at a different longitude.
Right.
Because the surface of the Earth is curved, when you get back to the equator, the spear is now pointing in a different direction relative to the ground, even though you never actively turned it.
Because the curvature of the Earth itself turned the path.
Exactly. That is parallel transport. It allows you to mathematically measure the hidden curvature of the space you are moving through. By putting orthogonal ON matrices on the edges of the sheaf, the neural network can essentially perform parallel transport between the tangent spaces of individual data points.
So the AI can literally feel the curvature of the data. It's not just connecting dots. It is mapping the invisible, multidimensional topology of the information.
It gives the neural network an incredibly rich, fundamentally geometric understanding of the underlying structure of reality.
That is just staggering. So sheaf theory gives us this brilliant topological way to compute local to global data structures without collapsing all our parameters like the Reynolds operator did on the standard graph.
Right, it preserves the complexity.
It lets the AI understand the deep geometry of complex heterogeneous data. But here comes another massive hurdle.
There's always another hurdle.
Always. What happens when the structures we are looking at aren't just large? What happens when they are literally mathematically infinite?
And that is the threshold where applied machine learning steps away from computer science and bleeds entirely back into the deepest, most esoteric realms of pure mathematics.
Because an AI has finite memory. A human brain has finite capacity. How on earth do mathematicians handle infinite complexity in a way that can actually be computed or proven? This leads us into our third set of sources, the advanced seminar notes from Bar-Ilan University and the deep dive into Sophic groups.
Right. If you pull back and look at the bigger picture, mathematicians have struggled with infinite groups for over a century. Infinite groups represent continuous symmetries, symmetries that never end and cannot be written down in a finite list.
It's just endless.
Exactly. So the concept of a Sophic group was originally introduced by the brilliant geometric group theorist Mikhail Gromov.
And the word Sophic has a very specific origin, right?
It comes from the Hebrew word sophi, which translates roughly to finite or end. The core philosophical idea of a Sophic group is dealing with massive, infinite, unmanageable mathematical objects by carefully approximating them using finite permutations.
Approximating the infinite with the finite. It sounds almost poetic.
It's highly practical. And specifically, the seminar notes focus on an extension of Gromov's work. Linearly Sophic groups.
Linearly Sophic.
A linearly Sophic group takes this idea and approximates the infinite group using finite dimensional matrices over a field. The formal notation used is GLNK, which stands for the general linear group of degree n over field k.
Okay, let's ground this. If I have an infinite mathematical group representing some mind-bending geometry that is way too complex for any supercomputer to process, I can try to build a sequence of finite matrices, little discrete grids of numbers that act like a shadow of that infinite group.
Right.
But here is my pushback. How do you know if your shadow is actually a good representation? If the thing you're approximating is infinite, how can you possibly measure the distance between your finite approximation and the infinite truth?
That is the crux of the problem and the genius of the specific metric they use to solve it. To measure the distance between two matrices, to empirically know if your finite approximation is genuinely getting closer to capturing the true structure of the infinite group, mathematicians employ what is known as the normalized rank metric.
The normalized rank metric. And the formula for this, according to the notes, is 1 over n times the rank of matrix A minus matrix B.
Correct.
Why rank? What does the rank of a matrix actually represent physically?
The rank of a matrix is essentially a measure of how much true independent information is contained within that matrix. If a matrix has a lot of redundant data, say multiple rows that are just multiples of each other, its rank is low. It doesn't have many independent dimensions.
Right.
By measuring the rank of the difference between matrix A and matrix B and then normalizing it by dividing by n, mathematicians have a highly precise, robust way to measure how functionally different these matrices are without getting bogged down by the sheer size of the matrices.
So they use this metric to build a sequence, matrix 1, matrix 2, matrix 3, all the way to matrix 1,000,000. And each matrix gets progressively larger, but progressively closer to mimicking the behavior of the infinite group.
That's the process.
But a sequence is just a journey. How do they actually capture the final destination, the absolute limit of this infinite sequence?
To capture that limit, mathematicians have to borrow a deeply complex tool from a field called model theory. It's called a metric ultraproduct.
The metric ultraproduct. I spent hours staring at this definition, trying to wrap my head around it. And the only way I could visualize it was by coming up with an analogy using digital photography. Tell me if this tracks.
I'm very curious to hear this.
Okay. Taking a finite matrix approximation of an infinite group feels to me like taking an infinite series of pixelated, low-resolution digital photos of a beautiful, perfectly continuous mountain landscape.
Okay, I'm with you.
No single low-res photo can capture the true, continuous reality of the mountain. It's just chunky pixels. But if you take an infinite sequence of these photos, each one slightly higher resolution than the last, and you feed them all into a mathematical ultrafilter, the ultrafilter essentially acts like a perfect voting system. It weaves all the overlapping truths from the discrete pixels together to perfectly reconstruct the continuous reality of the mountain. The ultraproduct is the continuous reality born from the discrete approximations.
That is a surprisingly accurate and evocative way to visualize an ultraproduct. An ultrafilter on the natural numbers does, in a sense, act as a strict voting mechanism that decides which properties hold almost everywhere across your infinite sequence of matrices.
It forces a consensus.
Exactly. It allows you to take the absolute mathematical limit of discrete, finite approximations and construct a new, massive object that perfectly captures the asymptotic properties of the entire sequence.
It's beautiful, but I have to push back here. Even with an ultrafilter, does this compression lose anything fundamental? When we force a massive infinite Lie algebra or a continuous infinite group into these finite matrices, are we just making a clever shadow on the cave wall? Or are we actually capturing the true, irreducible essence of the math? Like, the seminar notes mentioned this could solve something called Kaplansky's direct finiteness conjecture.
It captures the true essence. That is the sheer, astonishing power of linear sophicity. If a group is definitively proven to be linearly sophic, meaning it can be perfectly approximated by this metric ultraproduct of finite matrices without losing its core structural rules, then we can prove profound, overarching properties about the infinite group itself.
Because if the finite shadow obeys a rule, the infinite object casting the shadow must also obey it.
Exactly. Kaplansky's direct finiteness conjecture is a long-standing open problem in algebra regarding group rings. It asks whether A times B equals 1 inherently implies B times A equals 1 in these infinite structures.
Which seems like it should be obvious, but in infinity it's not.
Right. In infinite dimensions, it's not guaranteed. The source material highlights that proving a group is linearly sophic could, in fact, solve the conjecture for that specific group, because the finite matrix approximations rigorously retain that specific algebraic property. If the finite matrices are directly finite and they perfectly approximate the group, the infinite group must be directly finite.
Okay, so this brings us to the specific explication that we promised our listeners at Edward Little High. We need to unpack this incredibly dense mathematical statement from the sources.
The big conjecture.
Yes, the big one. Let me read it out word for word. If the image of G in the cohomological representation is linearly sophic, then the Hodge classes and the G invariant part of H to the 2p of x q are precisely those coming from algebraic cycles, if and only if the associated group algebra Q bracket G admits a separating family of asymptotically multiplicative finite-dimensional matrix models compatible with the Hodge filtration.
Okay, take a breath.
I know, that is a mouthful. But scholars, do not panic, because we are going to translate this into plain English, and more importantly, we are going to look at the practical implications of this being true.
Let's break it down piece by piece.
Right, so if the image of G in the cohomological representation is linearly so rough, we just talked about that, it means if we can take this massive continuous symmetry group G and perfectly approximate its topology using finite matrices,
Correct.
then the Hodge classes in the G invariant part. Now, a Hodge class is just a smooth, continuous, swooping geometric shape in this space.
Yes, it's a topological shape.
And we're looking at the G invariant part, which goes back to the very beginning of the episode. We are using the Reynolds operator concept to filter out all the noise and only look at the stable, unchanging essence of that shape.
Exactly.
Then it says these continuous shapes are precisely those coming from algebraic cycles. An algebraic cycle is a shape made out of rigid, discrete polynomial equations.
Like a circle defined by x squared plus y squared equals r squared.
Right, so it's saying if we can approximate the group as matrices, then we can prove that these fluid continuous shapes are actually built out of rigid, discrete math. But the catch is the last part. If and only if the associated group algebra Q bracket G admits a separating family of asymptotically multiplicative finite-dimensional matrix models compatible with the Hodge filtration.
Which is the core requirement.
What does that actually mean?
It means you can't just pick any random finite matrices. You have to be able to build a very specific family of matrix models, finite grids of numbers, that multiply together in a way that respects the deeper structure of the space, the Hodge filtration.
So practically speaking, what is the implication of this conjecture being true? Why does a high school scholar learning computer science care about this?
They care because it represents a literal bridge between continuous reality and discrete computing. If this conjecture is true, it means that the deepest, most fluid, continuous geometries of the universe, things that usually require infinite calculus to even conceptualize, can be perfectly modeled, approximated, and computed using finite arrays of numbers. Matrices.
Which means we can compute them on a computer.
Exactly. It means you can write code to understand the shape of the universe.
And that leads us perfectly into a practical exercise.
Yeah.
So Bus Sigma scholars, if you want to build further insight into this conjecture, how we can use finite models to find invariant shapes, we are going to guide you through a Python exercise using the CMU CS Academy sandbox in CPCS mode.
This is a great way to visualize what we've been talking about.
It really is. So if you go to academy.cs.cuu.edu/cpcs-docs, you can pull up a blank sandbox, and we are going to simulate finding a G-invariant shape using a finite matrix model.
Walk us through the steps.
Okay, step 1. In the sandbox, you are going to define your space. You can use app.background to set up a dark canvas. Now let's create our continuous fluid shape, our mock Hodge class. We can use the polygon function to draw a really weird asymmetrical blob on the screen.
Make it messy.
Exactly, make it super irregular. Now step 2, we need to create our finite dimensional matrix models. In Python, you can simulate this by creating a list of custom properties for rotation and scaling. We'll call this list our group G. So group G equals bracket matrix 1, matrix 2, matrix 3, matrix 4 bracket. Each one represents a different transformation like 0, 90, 180, and 270 degrees.
This represents our finite approximation of the symmetry.
Right. Now for the magic. Step 3, we are going to write a loop that acts like the Reynolds operator. Or, in the context of the conjecture, it simulates the Hodge filtration process.
By averaging the transformations.
Yes. You write a for loop that takes your messy polygon, applies every single transformation in group G to it, and then mathematically averages the coordinates of the resulting points.
And what happens when they run that loop?
When you run that loop, the code will draw a new shape on the screen. And because you averaged all the rotational transformations, the new shape won't be a messy blob anymore. It will be perfectly symmetrical. It will be the G-invariant part of your original shape.
You've essentially written a finite matrix model to extract the rigid algebraic essence out of a fluid shape.
Exactly. You are literally coding the fundamental principle behind this massive mathematical conjecture. It's just a Python loop, but conceptually, it's the bridge between discrete math and continuous topology.
It's incredibly powerful when you realize that the same logic scales all the way up to quantum physics.
Right. Because we also have these notes from the Les Houch's lectures on matrix models and topological strings.
Yes. This is where mathematical theory ties directly into the literal geometry of the universe itself. Matrix models are not just a clever algebra trick for group theorists or for Python exercises. They are heavily fundamentally utilized in string theory.
The lecture notes go deep into using double-line notation, where physicists combine fundamental and anti-fundamental representations of massive UN matrices. I read that part and got completely lost. How does combining fundamental representations actually help physicists understand the universe?
Well, in quantum field theory and string theory, interactions between particles or strings are incredibly difficult to compute. They form these massive, tangled diagrams. By representing the states using huge n by n matrices and using double-line notation, physicists can keep track of the flow of the mathematics geometrically.
Like drawing a map of the quantum interaction.
Precisely. And here's the connection to SOFIC groups. Physicists analyze how these massive finite matrices behave as the size of the matrix, n, approaches infinity. This is known in physics as the TUS limit.
The TUS limit.
Yes. As the matrices scale to infinity, they smooth out. Physicists can use this limit to compute the free energies of topological strings and literally resolve incredibly complex geometric problems, like Riemann-Hilbert problems using orthogonal polynomials. The continuous physical topology of the string is literally encoded in the discrete algebraic properties of the matrix approximation.
Which is mind-blowing. We're using the exact same philosophical approach, taking complex reality, vectorizing it, applying matrices, and finding stable invariance in the limits. Whether we are teaching a neural network to recognize a rotated number 4, running a Python script in CMU CS Academy, or using string theory to understand the fundamental fabric of the cosmos.
It is the universal search for discrete, algebraic shadows of complex, continuous geometric realities.
And that search for pure algebraic shadows leads us directly to the absolute pinnacle of our deep dive today, the final boss of modern pure mathematics, the Holy Grail, the Hodge conjecture.
The Hodge conjecture is not just a passing theory. It is one of the Clay Mathematics Institute's 7 Millennium Prize problems. A correct proof carries a $1 million prize.
That's a lot of motivation.
It is. But far more importantly than the money, a proof would establish a profound, underlying, undeniable unity in mathematics.
Okay, we need to take this very slowly because this is where the air gets incredibly thin. What exactly is the Hodge conjecture positing in terms that we can physically grasp?
Let's strip away the heavy jargon. Simply put, the Hodge conjecture posits that on a specific, highly complex type of geometric space, known as a projective complex manifold, certain topological shapes that exist within that space are not just arbitrary continuous fluid blobs. Specifically, it states that rational cohomology classes of type PP,
Which mathematicians usually just call Hodge classes.
yes, Hodge classes. The conjecture states that these Hodge classes are actually always built out of linear combinations of algebraic cycles.
Okay, I want to make sure the listener really sees the difference here.
Yeah.
A Hodge class is a topological concept. Topology is rubber sheet math. It's continuous. A Hodge class is a smooth, continuous, swooping shape defined by the sweeping calculus of the space. It can bend and stretch.
Correct. It is fluid.
But an algebraic cycle is a geometric shape that is strictly defined by neat, discrete, rigid polynomial equations. Like how the equation x squared plus y squared equals r squared perfectly defines a rigid circle.
Exactly. So the Hodge conjecture is stating something incredibly bold. It is stating that these specific, continuous, fluid, topological shapes, the Hodge classes, are inherently fundamentally built out of perfectly discrete, rigid, algebraic building blocks.
It bridges the gap. It proves that the continuous fluid world of topology and the discrete, rigid world of algebra are intrinsically the same thing at a certain level.
Yes. It implies that every valid topological shape in these spaces has a hidden polynomial skeleton.
And because proving this for every possible complex manifold in the universe is so incredibly difficult, mathematicians are currently trying to prove it piece by piece for very specific, highly complex spaces. Which brings us to the paper by Patel and Zhang on generalized prim varieties.
Patel and Zhang's work is an absolute masterpiece of geometric manipulation. They are trying to find algebraic cycles. They start with a continuous curve, which they denote as C, and to study the deep symmetries of this curve, they look at what is called a finite étal G cover of that curve.
Okay, an étal G cover. I think of this like a spiral staircase. If you look at a spiral staircase from straight above, it just looks like a flat circle. That's the curve C.
Okay, I can see that.
But the spiral staircase itself is the covering space. It wraps around the circle, but it unfolds the space based on a specific symmetry group, G. Locally, on any one step, it looks exactly like the flat circle, but globally it has a vastly richer structure.
That is an excellent visualization of an étal cover. By unfolding the space using the symmetry group G, they can analyze the curve in a higher dimensional context. Next, they look at the Jacobian of that curve.
The Jacobian. Let's define this simply. I think of the Jacobian as a mathematical ledger or a dashboard that tracks all the complex loops and holes of the curve, but maps them out into flat, manageable, linear space.
Precisely. It is an abelian variety associated with the curve. But the Jacobian of the entire covering space is too large and messy, so they mathematically decompose the Jacobian into a highly specific subbasement, an abelian subvariety called the prim variety.
And to figure out what is happening inside that prim variety, they use the group algebra Q bracket G, which is just a way of translating the symmetry group G into an algebraic field.
Right. And because the group G they selected is abelian, meaning the order of transformations doesn't matter, this group algebra naturally decomposes into a product of fields corresponding to the different irreducible representations of the group.
Stop right there. This is exactly what the sheaf theory did. The sheaf took complex data and broke it down into separate vector spaces. Patel and Zhang are taking the massive symmetry of the curve and breaking it down into separate, manageable fields.
It is the exact same fundamental strategy of breaking a complex structure into its irreducible components. Once they have these components, they use a highly specialized tool called the Abel-Jacobi map, combined with McDonald's formula for the symmetric product of a curve, to rigorously map the cohomology, the continuous topological shapes of the curve directly into the prim variety.
Okay. They build the spiral staircase, they build the dashboard, they isolate the subbasement, and they map the continuous shapes into it. But what are they actually hunting for when they do all that mapping?
They are hunting for Weil-Hodge classes, and here is the triumph of the paper. They successfully prove that these specific Weil-Hodge classes inside the prim variety come strictly and exclusively from algebraic cycles. They successfully proved a piece of the Millennium Prize problem for this specific geometric space.
But wait, how? How did they actually isolate those specific Hodge classes out of all that messy continuous math to prove they were rigidly algebraic? Did they just guess and check millions of equations?
No, they didn't guess. This is the grand synthesis of our entire deep dive today. To isolate those algebraic classes, they didn't look at the whole space. They looked specifically at the G-invariant part of the cohomology.
Let me stop you right there. Are you saying they used the exact same conceptual mathematical tool, G-invariance, that Bruno Ribeiro used in the YouTube tutorial to make a neural network recognize an upside-down number 4?
It is the exact same underlying mathematical principle.
That is insane. I am legitimately getting goosebumps. We went from an AI tutorial on a laptop to the absolute bleeding edge of pure math, and the key is the exact same.
It actually gets even more explicit than that. Look at the other paper in our stack by Salvatore Fliccari on hyperkähler sixfolds of the generalized Kummer type.
Hyperkähler sixfolds. I love these names. It sounds like a warp drive component on a spaceship.
It does sound sci-fi. It is a vastly complex, six-dimensional geometric manifold with incredibly rich symmetries. Fliccari is studying this space, and he specifically studies the LLV Lie algebra, denoted G of X, which mathematically acts on the cohomology of this space.
What is the LLV Lie algebra doing?
The LLV Lie algebra is a sprawling mathematical structure generated by what are called Celta 2 triples. These triples are deeply related to the Boville-Bogomolov form of the manifold.
The Boville-Bogomolov form. Okay, let's ground that. From what I read, this form is essentially a highly specialized mathematical ruler, right? It's a way to measure distance or angles between objects in these incredibly warped, multidimensional hyperkähler spaces without losing your frame of reference.
That is a brilliant way to describe it. It's a quadratic form on the second cohomology group that behaves similarly to an intersection form, giving structure and geometry to the abstract space. So Fliccari uses this LLV Lie algebra and this specialized ruler, and he is hunting for canonical Hodge classes in the manifold, specifically highly abstract classes denoted as C2 and QK.
And how does he isolate them? If he has this massive six-dimensional topological space, finding one specific algebraic cycle must be like finding a needle in a multidimensional haystack.
He identifies them by looking for the trivial subrepresentations of the Lie algebra action.
Wait. Think about what a trivial subrepresentation means. If an action is trivial, it means the action of the group leaves the object completely mathematically unchanged.
Yes.
That is exactly what an invariant is. It is a state that does not change when the transformation is applied. It is exactly like projecting the neural network weights into the eigenspace of the eigenvalue of 1 using the Reynolds operator. The weights don't change. The trivial subrepresentation doesn't change.
Exactly. It's the exact same mathematical phenomenon, just occurring in a six-dimensional hyperkähler manifold instead of a 784-dimensional pixel vector. Fliccari uses a structure called the Mukai lattice, combined with the LLV Lie algebra, to isolate these perfectly invariant canonical Hodge classes. And by analyzing this strictly G-invariant space, he is able to rigorously prove that they are represented by algebraic cycles, thereby proving the Hodge conjecture for these specific hyperkähler sixfolds.
So what does this all mean when we zoom out? We're using the mathematics of symmetry to strip away the noise of the universe. In AI, the noise is the spatial rotation of the image. The Reynolds operator strips that noise away by finding the invariant subspace, leaving only the pure geometric essence of the number 4.
Right.
In algebraic geometry, the noise is the fluid, continuous, unalgebraic topological curves. The geometricians strip that noise away by finding the invariant part of the cohomology, leaving only the pure, discrete polynomial structure of the algebraic cycles.
That is an exceptional way to summarize the entire philosophy of invariance. Symmetry is the universal filter. It is the master key to finding the fundamental, unchanging, rigid truths hidden within incredibly complex, chaotic, or continuous systems.
But why? I have to ask a philosophical question here. Why is symmetry the universal key? Does a geometric shape, possessing a symmetry, a stable, G-invariant state, does that inherently force it to have an algebraic polynomial backbone? Is the universe fundamentally, intrinsically algebraic if you just look at it through the lens of perfect symmetry?
That question is the philosophical core of why the Hodge conjecture matters so much. If the invariant parts of these continuous topological spaces are always undeniably algebraic, which the conjecture posits, it suggests that symmetry and discrete algebra are inexorably linked at the absolute deepest levels of physical reality. It implies that mathematical structure and symmetry are the very things that give rise to the discrete, rigid laws of physics out of the continuous boiling chaos of the quantum foam.
Wow. This has been an absolutely massive, mind-expanding journey today. We've covered incredible ground. Let's trace our steps back so we don't lose the forest for the trees. We started with the very practical, immediate engineering problem of teaching a neural network to see simple rotations without brute force memorization.
Yes, and we saw how Bruno Ribeiro used pure group theory, specifically the Reynolds operator and eigenspaces, to force a neural network to look past spatial orientation.
But we also rigorously examined the limits of that approach. We saw how the exact same mathematical operator caused a catastrophic collapse of the parameter space when applied to complex, heterogeneous, non-grid data like social graphs or molecular structures.
Right, the graph collapse. So to solve that, we upgraded our geometry to sheaf theory. We visualized assigning entire vector spaces to individual nodes using restriction maps as localized translators.
And computing the sheaf Laplacian to allow data to flow via heat diffusion until it naturally found a state of total topological consensus, or H0.
From there, we scaled our ambitions up to the infinite. We explored how Gromov's theory of linearly sophic groups uses the normalized rank metric and the voting power of metric ultraproducts to mathematically approximate infinite, unmanageable complexity using finite, discrete matrix models.
We even walked our Edward Little High scholars through a Python simulation of this using CMU CS Academy. And finally, we saw how those exact same underlying concepts, G-invariance, trivial subrepresentations, and isolating stable structural symmetries, are currently unlocking the deepest mathematical mysteries of the universe, allowing top-tier geometricians to prove pieces of the Hodge conjecture for prim varieties and hyperkähler sixfolds.
It is a stunning realization that the cutting-edge mathematics optimizing the neural networks on our laptops and the esoteric mathematics describing the geometric fabric of the universe are speaking the exact same language.
Which leaves me with a final, slightly terrifying, but incredibly exciting thought for us to mull over.
Oh, let's hear it.
If sheaf theory and G-invariance can flawlessly map the hidden fundamental topology of heterogeneous data inside an artificial neural network, and the Hodge conjecture implies a profound, literal bridge between continuous topology and discrete algebra in the physical fabric of the universe, could a sufficiently advanced, topologically aware AI eventually learn the mathematical mechanics of algebraic cycles?
That is the ultimate logical extrapolation of everything we've discussed today.
If we purposefully build neural networks that natively architecturally mimic the geometric symmetries of the math they are trying to solve, will the AI eventually discover the proofs for the remaining Millennium Prize problems completely on its own, simply by optimizing its own internal heat diffusion?
It's possible.
Will a future AI just naturally settle into a state of H0 mathematical consensus that just so happens to be the final million-dollar proof of the Hodge conjecture?
It is a wildly tantalizing possibility. We are no longer just building calculators. We are building digital architectures whose internal logic is rapidly converging with the structural geometric logic of reality itself.
And on that profound note, we are going to wrap up. Thank you for joining us on this deep dive into the source material. We invite you to look around you this week and keep questioning the shapes, the spaces, and the hidden symmetries of the world you live in. Because whether you are a silicon machine trying to read a wooden toddler's block, or a human mathematician trying to read the infinite geometry of the universe, perfect symmetry might just be the only answer key you ever need.